So we had finished diatomic molecules and by making molecular orbitals for them on Wednesday. We kind of had some complicated molecular orbital diagrams where we just looked at N2 and O2, right? Where we combined the valence orbitals of those two atoms, which are the two S's and the two P's together. And we were able to predict most of the properties that we expected. That nitrogen has a triple bond, right? That the p orbitals on either atom add together to form these pi orbitals. Right? What did we recommend? Nitrogen, we have just pull her up. Nitrogen has a single bond formed from the addition of the 2pz or the 2s orbitals on either atom. So again, I'll just write that. The idea is that either here's our nitrogens here, our 2pz orbitals if we're setting that the z-axis is the bond axis. Added together, we form a nice additive pair here. Or we can also take the 2s orbitals from nitrogen and add them together as well. Either way. We get a double single bond we get a regular old single covalent bond. And then we also notice that there are two sets of perpendicular orthogonal p orbitals on the nitrogens, each that has one electron in them. And we get this overlap that is perpendicular to the bond axis. Again, z is along this direction. So the bond is forming above and below the plane of the atom. The atoms rather, the line that separates the atoms. And there's another one that's perpendicular to it as well. But maybe this is the px and this is the py. Doesn't really matter what label you use. And we get constructive overlap outside of the bond on these kind of cylindrically symmetric where there's no density in the middle. We call these pi orbitals. There are two of them, and that implies two pi bonds. And we have a single bond, which we write sigma, right? Sigma for spherical. So nitrogen has two pi bonds plus one sigma bond to give us a total of a triple bond. Right? A bond order of 3. Right? Exactly like we expect from valence bond theory, old school general chemistry approach. Get a triple bond between the nitrogens, and then an oxygen. Oh, and then I'll write the labels here. So the most relevant molecular orbitals for nitrogen look like this. This is the pi star. This is the pi, and this is the sigma. This is kind of the area near the highest occupied molecular orbitals. This is sigma star. I apologize. Pi star, the antibonding orbitals. So this is nitrogen. Nitrogen's kind of what we call the frontier orbitals, the ones that are right at the point where you have this is the orbital with the highest occupied. That has the highest occupation, highest energy of occupied orbital with electrons in it, and then the first unoccupied one. We often call these, and I'll use this term a lot, HOMO and LUMO. And I'll define what those mean. This is the highest occupied molecular orbital. And LUMO stands for the lowest unoccupied molecular orbital. we'll use these terms a lot, and the reason why is that the HOMO and the LUMO kind of is where chemistry happens. Right? The easiest way to excite or move an electron, excite the system electronically, is to take an electron out of the HOMO and move it into the LUMO. Right, like that. That would be the first possible thing you could do with an electron. And so this is the lowest energy transition of the molecule, right? The lowest energy way possible to excite the molecule in some way. Right? So typically chemistry, right, relevant chemistry happens with these electrons, right? These are the chemically relevant electrons. All right, we're going to see that time and time again in the rest of this class, where we're going to really focus in on this HOMO and LUMO double couple, the pair, because that's where everything happens, right? I'll give you some examples as we go through the next 2 weeks of why understanding how the HOMO and the LUMO looks is really important for understanding how a molecule reacts. Right? The orbitals, there are more orbitals deeper than this, but we don't care about them so much because you have to have a lot of energy to really access those electrons. Right? These are the easiest electrons to access in the HOMO, so not surprisingly, most chemistry happens in that region. Now in oxygen, just quickly, the only important thing that happens is that in oxygen you have an extra set. Let me make sure I have the right ordering. Yeah, that's what I thought. So the switch, these actually switch in energy. Oh, sorry, these two switch in energy. So the pi, this is the pi star. This is the pi, and this is the sigma. Notice that they've, oops, sorry, I have that the wrong way. I apologize. No, that's right, sorry. This is the pi, sigma star, and sigma. This is what the frontier orbitals of oxygen looks like, and these are all filled up. So we have, compared to nitrogen, we have an extra two electrons in an antibonding orbital. All right, which means that now that the bond has an extra 2 electrons in the antibonding orbital, so the bond order is now 2, double bond. And the spins of the electrons in the HOMO are unpaired, which means that oxygen is magnetic. Right, so just by drawing these and playing around with them a little bit, we can come up with pretty much everything we need to know about these two molecules. Notice an interesting thing as well about oxygen is that its LUMO, which is a sigma star orbital, is different than it is for nitrogen. In nitrogen, you're taking an electron from a sigma orbital and putting it in pi. And in oxygen, when you excite the molecule, you're putting a pi electron into a sigma. So it's opposite the effect. So opposite kind of effects. And there's also this interesting thing that you can also have. There's also this state here as well. You can have these paired. This is what we call singlet oxygen, slightly higher in energy. But we don't have that luxury here in nitrogen. This is still kind of a electronic ground state. Our electrons are in the original orbitals they were. They haven't moved at all. We've just changed the spin orientation of them. Now they're paired instead of unpaired. Right? So this is still basically the same state, but we have a different state, right? We have a different identity. It's a different molecule altogether, what we call a spin isomer. Right? We go from singlet to triplet Right? We're not actually formally exciting the molecule in any way. We're not moving an electron from one orbital to another. We're just flipping its spin. So oxygen has this singlet and triplet orientation. But nitrogen, you don't have that luxury, right? Everything's paired in nitrogen. So you can't flip anything. Right? You can't put two electrons with the same spin in the same orbital. That's no go. It's impossible. So the only thing you can do with nitrogen is excite an electron up to here. Right? You can excite from the HOMO to the LUMO. That's the first thing that you can do energetically to nitrogen. That takes a lot of energy. But you can, in oxygen, you can spend a little less energy and do something interesting to the molecule to convert the triplet to singlet. That's less energy than exciting the molecule up to the sigma star, this energy difference. So oxygen kind of has more flexibility, if you will. Right? There's more things oxygen can do. There are more configurations oxygen can exist in at a given temperature than nitrogen. Nitrogen is very simple. And that also explains why oxygen is quite reactive compared to nitrogen. So nitrogen, to do anything, to destabilize nitrogen at all, you have to take an electron from here and promote it up to the pi star. You have to really weaken that bond. That takes a good amount of energy to go from here to here. Right? This is UV energy. But to go from here to here is much lower energy. Singlet oxygen is very reactive. And energetically accessible. So oxygen in general, just from its molecular orbital diagram, implies that it has more reactivity, right? It can do more stuff. Right? Its electrons can exist in many different ways. They can move around. The electrons can move around, which you can't do with nitrogen. Nitrogen, you're just kind of fixed in place. Right? So nitrogen is very inert, and oxygen, again, is it super? It's inert, but not really. Actually, I would not call nitrogen an inert molecule. So you combust. You can't really combust nitrogen. Right? And this is the reason why. Is oxygen has these unpaired electrons. They're in pi star orbital, antibonding orbital. They can move around much more freely. Right? Much more free electrons. Right, so oxygen in general is much more reactive. Now if you go to fluorine, F2, we don't really have to change that much. We're in red, we just have to add 2 electrons here. Fluorine, again, now you have full everything. And so fluorine you would expect to not be that reactive. But the thing is that now you have 2 extra electrons in this antibonding orbital, so fluorine has a single bond. It's much weaker, right? It's a much weaker bond than oxygen or nitrogen because now you have 4 electrons in the antibonding orbital. So you basically cancel out this pi system, right? This pi system doesn't work anymore. This is, right? You have the same number in pi stars you do pi, so these cancel out. And you're just left with a single bond. And so fluorine naturally is weaker because it doesn't have these pi bonds to strengthen it. So fluorine tends to fall apart really readily. It's also a lower energy for an electron to be excited here in fluorine from the pi star to the sigma star than it is for sigma star to pi star in nitrogen. So this is a big energy gap. And this one's smaller. All right, so you need less energy to promote that electron and excite it. And also the bond is weaker because now your pi stars are completely filled and you're left with a single bond. Okay, so just by putting electrons into these orbitals, I can make lots of qualitative assessments about the stability of molecules in this way. Any questions about that? Okay. Give me just a sec. I'll give you guys a sec to catch up. I want to move to a different molecule today to kind of finish up. This will allow us to, hopefully if we have the time, this will set us up for what we'll be doing for the rest of the semester, which are hydrocarbons. So I want to talk about the classic hydrocarbon first, which is methane. Methane's a very interesting molecule. All right, so let's talk a little bit about what we know about methane. So we're going to, instead of assuming nothing about it, let's at least figure out what we know about methane. First of all, is that it has a tetrahedral geometry. Something like this. Like that, and of course all the bond angles are equivalent, the bond lengths are equivalent, they're all 190.5 degrees, and the bond lengths are like 1.5 angstroms, I don't know what they are exactly. Right, everything's equivalent. I can tell I'm getting near the end of the semester, all my pens are dying. 4 equivalent hydrogens. Right, all 4 hydrogens are exactly the same. Right, you just have to rotate this molecule and you generate the same molecule again. There's lots of different ways to move the molecule around to generate the same structure. And this means 4 equivalent bonds. And we have this idea from general chemistry or organic chemistry, which is this idea of sp-d hybridization. Right, the orbitals, the bonds of these have some s and p character in them. Right, I want to talk a little bit about this hybridization scheme very generally, about how it's constructed, how we learn about it in organic chemistry, and then I want to show you how it's wrong. I mean, it's a good prediction, but it doesn't predict everything correctly. So the idea was, so Linus Pauling, one of the great original quantum chemists, says right, that we have 4 hydrogens all in the 1s state, right? Regular old hydrogens that we're adding together. We have a neutral carbon, which has 1s2, 2s2, 2p2. But the problem with this construction that is if we add, for instance, if we look at carbon's p orbitals, I'll just kind of draw them all together. We'll call this the px, this is the py, and this is the pz. Just add them on top. They're arranged in the wrong way for tetrahedral geometry. All of these, the PZ, in this case the PZ and the PY, let's see if I can draw it, are all in the same plane. And then you have the PX orbital or the PZ orbital, however you want to call it, out of the plane. Right? So you have like a square of 4 lobes. Each edge is a lobe of the p orbital. It's a square around the carbon. And then your third p orbital stands above and below it directly. So that doesn't match my geometry at all. I'll redraw it just to compare. Right? This does not help me at all. If I just add hydrogens to these p orbitals, I get the wrong geometry. Something like that. And if I overlay hydrogens, if I overlay the hydrogens in this arrangement, I'm going to have one here. But then my other ones are down here. Kind of hard to see, but they're in between. And then I have another one right here. Right, so methane is not just 4 hydrogen 1s plus carbon 2p additions, because it doesn't give you the right geometry. The p orbitals are in the wrong direction. They're planar, and then you've got one above and below, but it doesn't give you the tetrahedral geometry that you want. It's not really obvious from this picture, but it's more like the other one is here, something like that. Right, they're just not in the right place. So what Linus Pauling says is a really clever idea. Is a really clever idea. Pauling says to add things together. Right? Let's make a more interesting combination of our orbitals than just the p's. Let's let my carbon wave function, so the wave function for my carbon atomic orbitals, to be a sum of its 2x and 2p's. I'm just going to write pluses or minuses. All right, so this is the carbon atomic orbital that we choose. So what we're going to do is add a little p and a little s together. And in fact, what we're going to do is 75% p and 25% s. Right? We're just going to do an equal add to all of them. We're going to add them together and pick the right signs. And this will actually give me the right geometry. It's kind of hard to see that. You'll just have to trust me. But when you add the orbitals together, when you treat the s's and the p's as one's unit that you sum together in what we call a hybrid orbital, right? It's not a pure orbital, it's a sum of atomic orbitals. What we get is that in the atomic orbital basis, so without adding them together, carbon looks like this. I'll draw the orbitals on top of it. So there's our 2s orbital, and then we have 3 2p's. Let me draw this right. Yeah, like this. So here's our original atomic orbital basis. This is just regular carbon. Got 2 electrons in the s orbital and 2 in the p electrons, and then when we add them together, when we hybridize, add them together in the way that Pauling does, by 75%, 25, just like this way, you get through 4 new orbitals, because we've added 4, we get 4 out, that have the correct geometry. They actually rotate slightly away from the axis of the system, the XYZ axis, and give us the correct orientations that we want. Let me draw this a little more properly. I want to notice that, again, they're not, no longer are they equal in size, but they kind of have an extra large lobe on the outside of them. They have a small lobe, a large lobe, and the lobes are now directed at angles instead of perpendicular to or parallel to each of the axes of the system. All right, it's not hard to add these together and show that the lobes rotate like this when you add them together. So we call these sp3 orbitals. Nice. These are our sp3 orbitals. So now our carbon valence has a different shape, if you will. Instead of adding s's and p's together, we mix the s's and p's and carbon together to get these new sets of orbitals. And then we can add 4 hydrogens in their 1s orbital to get us tetrahedral methane. Something like that. But here's the problem with this analysis. So Pauling does this in like 1920. And when you calculate, when you add the right combinations of things together and weigh them 25, 75 like this, you get the right directions. You get 109.5 degree angle between the orbitals, right? And everything looks great. But there's a problem with this. There's a problem with this construction. The problem with this construction is that all 4 of these orbitals, so when I add a hydrogen to them, again, they all fill up. So if I add an H, to them. That's my H in blue. I have 4 bonding orbitals all completely filled up, which is great. But they're all equivalent. They're degenerate. Okay? So what that would imply is that my HOMO, in my molecular orbital theory, my HOMO are 4 orbitals that are really, really close together. These are my sp3 plus H orbitals. 2, 3, 4, 5, 6, 7, 8. And then my LUMO, I don't want to put these all, I want you to remember that these are all same energy. Would look like this. You'd have 4 orbitals as your HOMO that are completely filled, and this would be sp3 minus H. The anti-bonding combination, if you will. Sigma star, this is sigma, more or less. That you would have 4 orbitals up here that are unfilled, they're all the same energy, and 4 orbitals here that are degenerate, that are filled. Okay, so what happens then if you were to, so one of the interesting things that disproves that this is correct is that if you were to calculate how much energy it would take to remove an electron from the HOMO, we would get one answer, right? Because all of the electrons, all 8 electrons are in the same orbital, they're same energies, in 4 different orbitals, but they're all same energy. So in a spectrum of ionization potential, ionization energy versus electron flux, right? How many electrons you get out as a function of energy, you're just going to get one peak. Because all the electrons have the same amount of energy. It takes them the same amount of distance to the ionization limit. So if I were to plot, if I were to shine a really, really bright light at my molecule, so Pauline's scheme for bonding MOs that are 25% carbon 2s and 75% or 2p character, all same energy. If I were to plot or take a spectrum of electron flux versus energy in terms of EV, right? I'm going to shine a high light at my molecule until it absorbs that energy and plucks an electron off. Pauling would say that there's only one peak. Of 8x sigma electrons, right? They all get ionized at the same energy, right? Because they all have the same distance to the ionization limit, right? So you just see one peak, However, experiment shows a different answer. First, you see a peak at 14 EV. That's quite strong. And then you also see one at 23. That's a little weaker. Like this. There are 2 peaks. What that means is that the valence electrons in methane exist in 2 different types of orbitals. right, so in fact, again, we've accounted for all the valence electrons with Pauline's scheme, all the valence electrons of methane here. This is all of them, all 4 1s's and all the 2s's and 2p electrons for carbon. Says that they're all the same energy degenerate, so they all have the same ionization potential. But in real life, there are 2 bunches of them, one at 23 eV and one at 14. Right? So that must mean that this is wrong, right? Because this predicts the wrong structure. Right? This predicts 4 degenerate orbitals, but in fact we have 2 sets of orbitals. Right? So we've done something wrong. All right, and the Pauline's mistake was very subtle. And, you know, I feel bad for Linus Pauling. He certainly deserves his 2 Nobel Prizes. It's not a crock. He just didn't understand the system completely. And it wasn't until later that people understood that there was a different way to construct things that was more physical. That gives us the right answer. So I want to talk a little bit about that today. Finish that up. So let's talk about how we more properly construct methane's orbitals so that we get the right predictions. Right? The valence orbitals all sit in either 2 different types of orbitals. One that's higher energy and one that's lower energy. So what I'm going to do is I'm going to take advantage of the fact that I know that methane is tetrahedral and all its bonds are equivalent. Right? So the way I'm going to do this is quite simple. I'm going to draw a box. A tetrahedral system will embed itself in a cube quite easily. That's why it's called tetrahedral. So if I were to draw a box like this. And then what I want to do is I want to place my 4 electrons as far away as possible from each other on the vertices of this box. Right, so the electrons, or sorry, let's say hydrogens rather. Hydrogens sit at the vertices of the box, like these little dots, right, where multiple edges meet. Sit at vertices of cube, and maximize their distance apart from each other. They want to be as far apart as possible, but we need to maintain the symmetry of the system, which is a cubic symmetry, tetrahedral, and so they're going to have to be at 4 different vertices that are equidistant apart as far as possible. And there's only one way to draw that effectively. So you could put a hydrogen here. I'll draw them in red. If there's a hydrogen here, there's going to be a hydrogen over here, and then there's going to be a hydrogen here. A hydrogen here. All right, you can look, all the hydrogens are 2 edges apart. 1, 2, 1, 2, 1, 2, 1, 2. Right, they're all 2 edges apart. This is the furthest apart they can be. All right, so what I'm going to do is I'm going to fix my hydrogens there. So these are our hydrogens in the edges of the box. This satisfies all the symmetry properties of methane that I want. And then what I'm going to do in the middle of the box, I'm going to put my carbon. All right, so this is how I'm going to construct my molecular orbitals. Now what I'm going to do is construct my bonding MOs for methane by combining my C2s and 2p orbitals with my 4 hydrogen 1s orbitals. Okay, so my 4 molecular orbitals are going to look like this. It's a sum, plus or minus a sum, of my 4 hydrogen orbitals, plus or minus the carbon 2s orbital. And then I'm going to do the same for all the other ones. So this one, this one, this one, this one, plus or minus psi 2px, c, this one, this one, this one, this one, plus or minus psi 2py, c, this one, this one, this one, this one, plus or minus psi 2pz, c. Okay, so my construction now, so Pauling, again, what Pauling did was add all of the carbon orbitals together. Right? His construction are putting all 4 top carbon orbitals together into a set of 4 different molecular orbitals. We're doing something different this time. We're going to combine all 4 hydrogens together with one of the carbons. So we're hybridizing, instead of hybridizing the carbon orbitals together, we're hybridizing the single carbon orbital with the hydrogens together. Right? It's a slight difference. Okay, so I'll just write that. Pauling hybridize C orbitals and then add hydrogens. And what we're doing is add hydrogens to single C orbital and then hybridizing, and then adding them together. All right, so we're kind of doing it a slightly different way. All right, so geometrically I can show how this works very easily. So the first thing to note is that hydrogen or orbitals, and I've kind of implicitly said this. Let me write it in the big one. Orbitals can be added or subtracted. And the way we add or subtract is by phase. So for instance, 2s, the orbital, I'll often write it with this like this. I could write it like this. This is what I call a positive phase. This means the wave function is positive. Or we can write it like this, negative, right? So this is a negative function. Or a subtraction. Right, this is what I mean by subtracting an orbital, is I add the orbital the opposite sign. Right? And the 2 p's look like this. So this is the plus combination and the minus. It has 2 lobes. It changes sign of the electron. And there's an equivalent orbital that I can write where the signs have changed. Okay? So I can add orbitals like this any way I please. And the bonding orbitals are ones with maximal overlap. All right, we're going to try to match the colors as much as possible. Right? So where there's the plus, we want the height. If there's a plus 2p, if the carbon 2p orbital is in the middle of the box, and it looks like this, we want to make sure the hydrogens above the carbon are matched with this color or the shading, and aren't matched, and the ones below it are matched with the negative sign as well. I'll show you what I mean by that as we go through this. So super easy to construct these. Once you see one, you'll understand exactly what I'm doing. So the first one I'm going to draw is the easiest one to figure out. Here's my nice cube. And then what I'm going to do is I'm going to put my carbon 2s orbital in the middle. Here's my carbon 2s orbital. Again, I can choose any color I want. This is my 2s. All right, and then on the edges, which we've already defined, I have to add hydrogens to them. And I want to add hydrogen, the signs of the hydrogen wave functions. Again, these can be plus or minus, right? They can be like this, or they can be like this. Either this means subtraction and this means addition relative to the other color. So in this case, if I'm adding hydrogens to it constructively, I want to add hydrogens that are shaded. If I want to subtract a hydrogen, I want to show one that's the opposite sign of this so it'd be clear. All right, now I want to build bonding MOs. So I want to do ones that have maximal overlap. So I want my hydrogens to be able to overlap with this 2s as much as possible. So there's really only one way to do it, is to take all the hydrogens, just got a plus to them, right? They're all the same sign. Where am I missing one here? And one here. All right, so this is effectively, this MO is 2s plus 4, 1sh, right? All right, and there's a corresponding, so this is bonding, because everything overlaps each other, right? This H, again, the sizes are to scale aren't to scale. This is just a figure, just a figurative approach to it. But again, these overlap constructively. They all overlap constructively together, right? So this is a bonding MO, and there's a corresponding anti-bonding one. Or again, I'll just leave the 2s orbital of the carbon the same color, and then I'll just make all the other ones negative. Right, so this is psi1 star, which is psi2s minus 4 psi1hs. Right, here they all cancel out. Right, none of them like to talk to each other. So that's really easy to do. All right, now we have to deal with the p orbitals. So we have 3 of them. And I'm just going to draw the bonding combinations just to save time. We don't have to worry about the anti-bonding. We know they're there. So now this is the carbon 2s. Carbon 2p. I'll draw 3 boxes, one for each carbon 2p orbital. So now I'm going to put my p orbitals in the middle. Again, I can make any choice I want. I'll just draw it like this for this one. Draw it like this. Oh, that's the wrong way, sorry. Draw it like this for the other one. And then there's one out of the board like this. Okay, and now I have to draw my hydrogens around it. Again, I put them in the same position as before. Hydrogen here, hydrogen here, hydrogen here, and a hydrogen here. And now I want to shade my hydrogen so that I have maximal overlap with my p orbital that's inside. Well, this one's really easy. We have the plus. If you think the plus sign of this lobe is up, so that must mean that these must be up as well, and these must be negative. Like that. Okay, and then we can look at this one. These must be positive, right, because they're on the positive side. And these are negative. Huh? And then we have this weird one right here. Again, this is in and out of the board. So the ones in the back should be negative, and the ones in the front should be positive, right? So these connect like this. All right, so this is like, let's call this, I don't know what to call this. We'll call this 2pz, 2px, and 2py. So this wave function, psi3, or psi2 we'll call it, is psi2pz carbon plus 2 1HS minus 2 1H, or sorry, 1SH, sorry. It's a little bit of dyslexia. All right, we should label these. I'm going to label them 1, 2, 3, and 4. So this one is, the positive combination is 1 and 2. And this is 3 and 4. And then this one is psi 3, psi 2px plus 2 psi h1s. And what numbers are those? That's 2 and 3 minus 2 psi h1s 1 and 4. And this one is psi 4 psi 2py plus 2 psi h1s. What units are those? This is 2 and 4 minus 2 psi h1s 1 and 3. Okay. So again, all I've done is I've done the most naive thing I can possibly do is put my hydrogens, fix my hydrogens in a tetrahedral geometry, and then just add my orbitals as simply as possible, right? Just color them based on having maximal overlap. These are my new bond fields. Okay, so now here's the interesting thing about this. This one over here is unique. How many constructive overlaps do we have between the hydrogens and the carbon? We have 4 identical overlaps. Right? We have 4. They all overlap constructively. And then what do we have over here? We have 2 pairs of constructive overlaps. With a node, with a nodal plane. Right? That's where the sign changes. Okay, there's a really interesting, and we'll see this when we get to on Wednesday, there's a really interesting kind of, it's not really a theory, just kind of an observation. But observation is when constructing or mixing orbitals, the combinations with the least amount of nodes or sign changes are lowest in energy. Okay, so let's think about where does the sign of the wave function change here? Well, it doesn't. It's all positive, right? Or it's all negative. Yeah, it's all negative. Or well, actually, this one has 4, right? It has 1, 2, 3, and 4. This has 4 nodes. This is really high energy. This has 0 nodes. Right? Everything is added together. Everything's the same sign. And let's look over here. Well, we have a node between these. 2 nodal planes. And they also go like this as well. Right? And if you look at all of these, they all have the same nodal surface. These all have the same number of sign changes. Now, when we talk about hydrocarbons next on Wednesday, we'll see this. We'll be able to do this analysis much more easily. We'll look at rings in particular. But it's not hard to convince yourself, if you're geometrically associated, it's not hard to convince yourself that these are all identical. If you take, for instance, this one and rotate it like this, rotate it clockwise 90 degrees, you get this one. Right? You see that? Right? It's the same one. And likewise, if you take this one and rotate it this way out of the board, you get this one back in a little bit of a rotation as well. Right? So you can rotate each of these and get the same one back. They're all identical by a rotation. All 3 are identical by rotation. What does that mean? It means that all three of these, they have the same amount of sign changes and they're all identical. All three of these orbitals are degenerate. Okay, so we have a triplet of molecular orbitals that are all the same energy. And then we have this new one that we've also added, this one that is unique to itself. This one is completely different from these, right? Because these have sign changes, this one doesn't. This has no nodes. This is kind of the most bonding orbital. So we have two different classes of bonding orbitals. We have these triply degenerate ones, and we have the singly degenerate one by itself that's lowest in energy. So the molecular orbital diagram of methane looks like this. There's my two P's. Just as a reminder, this is at minus 22 eV, and this is at minus 11.7 eV. And our 1S's are at minus 13.6 EV. Okay. This is hydrogens. There are one electron per each one. And we form a pair of triply set of degenerate orbitals and one that's by itself that's really bonding. All right, so this one has 0 nodes, so it should be lowest in energy. It comes from the bonding of the 2s of the 2s plus the 1s orbital. That's this one right here. All right, and then we get an equal and opposite antibonding orbital. Let me draw these with dashes instead. All right, and then what do these look like? Well, it's really easy to draw this like this. That's our symmetric combination of all the orbitals. That's the most bonding one. And then we have this triplet set that forms where we have a bonding interaction, right? Two of the atoms kind of bond to one lobe and the other two bond to this lobe. So they're still bonding, but they're not quite as bonding as the sigma orbital. 1, 2, 3. And likewise, we get an anti-bonding set as well. 1, 2, 3. Like so. Okay, and what do these orbitals look like? Let me draw them in a different color. Oh, that one's good. So, for instance, this one might look like this. One that looks like that, and then there's the other perpendicular ones as well. I'll try to draw them. This one's really kind of easy to do. Like that. And then there's one that's like, this is one where it's pointing out of the board. These are our pi bonding orbitals, the ones that add from the p's, right? This is the 2p contributors, the 2p carbon orbitals, hybridized. So let's fill it up. We have 1, 2, 3, 4, 5, 6, 7, 8 electrons. So all the bonding orbitals get filled. Right, so we expect a bond order of 4, right, because we have 8 divided by 2. There are 4 bonds, so they're each single. So the bond order, total bond, is 1/2 8 minus 0, which is 4. So per bond, 1. Right, single bond. All right, so we have 4 single bonds. They're all equivalent, and they're tetrahedral, like we constructed. All right, you get an orbital diagram that looks like this. Now it should be obvious why we get 2 peaks from our ionization spectrum. We have one, if I put my vacuum, if I put the ionization limit here, I have one there, a peak that goes from there to there, which is at 14.8 eV. And that's how much that's the ionization potential of hydrogen or of methane, 14.8. It's these electrons being excited. But if you really juice the heck out of it at 25.7, you can get electrons from this core bonding orbital as well, this really highly bonded molecular orbital that we constructed, right? So we predict 2 ionization peaks in the valence, not 1. All right, so when the photoelectron spectra of methane came out, it really threw quantum mechanics for a loop, right? They had been spending years doing Vesper theory and all of the hybridization, all this old junk that we learn in general chemistry, and it works, right? I mean, Pauling's approach worked and predicted the tetrahedral geometry, but what he predicted is that all of these orbitals are at the same energy, right? But he didn't account for the fact that they can, this idea that instead of hybridizing it where you fix the hydrogens, you actually find out that there is a bonding combination that has 0 nodes and a set that has multiple nodes that are all equivalent. And that causes the spacing, the splitting. So now you don't have 4 degenerate orbitals, but you have a set of 3 and then a 1 by itself. Right? And this gives us all the properties of methane M1. Right? This is experimentally accurate. Okay, so what we'll do on Wednesday, I'll probably just stop now, is we'll put 2 methanes together to make, well, we won't make ethane, that's not that interesting, but what we'll do is we'll look at ethylene, C2H4, all right, let me write this. Actually, let me do this as a hint, like going forward. So, like a spoiler for tomorrow on Wednesday, next class. We'll look at ethylene. All right, we'll do the same kind of idea that we did for methane, but now we have it's actually a simpler molecule. We have more atoms, but this is planar. And of course, it has lots of symmetries in it, right? We have a symmetry plane here, we have a symmetry plane here, symmetry plane here, symmetry plane here. All 4 hydrogens are equivalent. And of course, the carbons are as well. And what we're going to find is that the HOMO for this system is a pi bonding orbital fully filled. So this leads to a bond order of 2 for the carbon-carbon bond, as we expect. But the LUMO, it's just the next orbital up that doesn't have any electrons, is a pi antibonding orbital. All right, so and it turns out that it doesn't matter how big your construction is, all planar and conjugated organic molecules. So molecules with double bonds and pi systems, we'll talk more about those, have a pi star HOMO-LUMO characteristic. So the orbitals that are at the top, so for molecules like ethylene or butadiene or benzene or naphthalene, or not naphthalene, or pyridine, all of these molecules, doesn't matter, their HOMO is a pi orbital and their LUMO is a pi star. Right? They all have the same character right at the top of the energy level. Right? Their HOMO is all pi electrons and their LUMO is pi star electrons. And so when we get to conjugated systems, the only two orbitals that really matter, right? We don't even have to worry about these deep ones. We only have to worry about the pi ones, the ones where the pi's add together to form a double bond. Right? These pi orbitals that form above and below the plane of the molecule. So what we can do is simplify our analysis, and instead of, say for benzene, instead of taking 6 equivalent hydrogen atoms and hybridizing them with 6 equivalent hydrogens, we just ignore all of that. And instead what we're going to do is only care about the region of the molecular orbital diagram that is the HOMO and the LUMO. So benzene, what we're going to look at are these pi orbitals that are perpendicular to the axis, like this. Right? This is the conjugated system, right? We're going to look at the molecular orbital diagrams of just the pi orbitals, or the p orbitals, perpendicular to the plane of the molecule. All right? These are always involved in the HOMO and LUMO interactions, right? The HOMO and the LUMO are always in these conjugated systems, these pi orbitals like this that are perpendicular to the plane. All right, so we can look at the HOMO-LUMO region by taking benzene's wave function to be a sum of these 6 2p orbitals on each of the 6 atoms. I'll label them A, B, C, D, E, F. All right, we're just gonna construct molecular orbitals out of these p orbitals that are perpendicular to the ring, and do some simplifications to come up with some really easy math approximations to how to calculate the different molecular orbitals of these systems. You can do it in Wolfram alpha. It's really easy. We'll do some simplifications to make the math easier, and we can learn everything that we want to know about conjugated systems and predict their stabilities, their relative stabilities, and isomer characteristics and other types of effects, including their electronic spectra, by just considering the 2p orbitals that are perpendicular to the plane. All right, so we'll get rid of all the hydrogens. We don't care about any of those things because hydrogen bonding between a carbon and hydrogen tends to be very, very low energy. Right? We really care about the ones that are right at the top of the energy levels. And those, for high conjugated systems, those are going to be the p orbitals. So we're going to stop adding hydrogens and all the s orbitals and the p orbitals, all the valences, and just focus in on just these p orbitals and how they add together in a ring system or in a double bonded system like this. We'll come up with some really some simplifications on how to do the math, and we'll have a general theory that allow us to predict all sorts of things about these conjugated systems. All right, so that's what we'll start on Wednesday. All right, homework 4 has been posted. It's due May 1st. I'll have solutions for Sean tomorrow. It's all on molecular orbital theory. You can probably do one or two of the problems right now if you wanted. Some of them will, the other two problems, the other half, it's 4 problems, I think. The other half requires a little bit of knowledge about this p orbital scheme that we're going to do. We're called Huckel molecular theory, orbital theory. We'll start that on Wednesday. So by next week, you'll have pretty much all the skills you need to finish it. Probably by Wednesday. Over the weekend, you should be good. All right, guys, have a good one.
Have a good one, Dr. Seifert.
You too, thank you.